Hello fellow problem solvers. So today we're going to be doing a problem from the 2022 IMO problem number 5, a number theory. And guess what? A classical one. It's not that fake number theory that's really a combinatorics. It's a number theory. And I suggest you try this one out for a minimum of 20 minutes, ideally 90 to maybe 2.5 hours. I wouldn't do this more than 4.5 hours. You wouldn't have that much time at the IMO anyway. And it's a phenomenal problem, especially if you're feeling good technically with your number theory, like on a technique level. And I just want to point out with this problem, also if you want to go along with us, pause for the next 5-10 minutes and get your first ideas out on paper. And what I like here is, mind you, I've recorded before this, so I'll release later, the JBMO from 2022. And there's problem number 3, and it's also a, b, a prime, and another prime there, but it's a similar thing like we're dealing with primes. Yoo-hoo. So, and I think it might have been also a to the power of prime. So could that be useful somehow? Is it good to solve other problems from other competitions which are of a similar level? Maybe. Like maybe it's going to be useful, but definitely it is. So how are we going to approach this is the first question. So when you see this, you're like, whoa, wait, what? Like how am I even, like, this is a to the power of p, b factorial, then I have a plus p? Like what's happening there? How do I even begin? And now here's my question to you. And this is a heuristic that I've covered on this channel a lot, and I'm going to continue covering it. And the question is really, if you don't know what to do, you start off with a problem. It's a problem number 5 at the IMO. You solved number 4, you've watched some of my geometry videos, you're now good at geometry, you solved it, and now you're left with number 5. And they're like, whew, what do? I don't know how to begin. What do you do then? The answer is, you play around with small cases, explore the problem, but play around with small cases. If you have no idea what's happening here. Now, what does that mean here for us? Well, let's just, plug in some specific values. Now, for what? Like, what are we going to plug in specific values? Like, in which order? Are we first going to plug in A, then BP, or PAB, or PBA, or PAB? Like, what's the order in which we're going to be plugging stuff in? Okay, pause for 2 minutes and think about that. And for me, the answer is, well, let me try P, right? Because the A and the B are, like, this is my constant term, so to speak, and I've solved problems that are similar to A squared is B factorial plus 3, right? That's a problem I've done before. And so I'm thinking, maybe I can, finagle my way, but just like setting this constant term out and then look at the relationship between these two. So if you haven't, I invite you to pause for 5 minutes and play around with some smaller values. And so let us now do that. So we have p is equal to 2 is one case. And then this becomes a squared is b factorial plus 2. Do you know how to solve this? Say again that you don't know how to solve it. What would you do? You would play around with some more values. Okay, so let's plug in which one, A or B? Well, here's the reasoning now. If I'm plugging in A first, plugging in different values of A, like I'm really saying that a squared minus 2 is equal to b factorial. So I'm saying that if I'm plugging in different values of A, I want to get the right b factorial. And it seems like I'll need to specifically hit all the factors, which is one thing I'm not sure of. And actually for 2 there, I might be able to do some quadratic residue stuff there, that I might miss a factor definitely at some point. But that's a bit maybe overly complicated to begin with. But if I'm doing it the other way, I have a lot of factors here, plus a 2. I know roughly what's on this side and what's more on this side. And if we don't even need to go through the reasoning, we can just like plug one after the other. But now if I plug in, say b is equal to 1, I get a cubed is 3, a squared is 3. This fails, not a solution. If I plug in b is equal to 2, what do I get? I get a squared is 2 plus 2 is 4. So a is equal to 2, and now we have a solution. Let's write those down. So a, b, p, one solution is 2, 2, 2. Okay. What about b is equal to 3? What do I get? I get a squared is 2 plus 6 is 8. Fails. I keep getting like even stuff here. Why is that? Well, now 2 divides b factorial now, and it divides this, so it divides their sum. It's even. And here I have an 8, which is really one more extra 2 that's messing me up. So now what about, say, b equals 4? What do I get? I get a squared is 2 plus 24, which is 26. Now this is 2 times 13. It also fails. But now it fails why? Well, I have a factor of 13. Sure, but I also just have 1, 2 now. Right? That's something that's changed a bit. And now I can solve the problem for this case. Pause for 5-10 minutes and try, like 2 minutes really, and try to think about this. And the answer is, well, if b is greater than or equal to 4, then we have also like 2 divides b factorial plus 2, which is equal to a squared. So 2 divides a squared. So 2 divides a. So 4 divides a. And now combine that with 4 divides b factorial from here. This implies that 4 divides a squared minus b factorial, which is equal to 2. And that's a contradiction. That's nonsensical. 4 does not divide 2. So, for p is equal to 2, this is our only solution. Now, can you go to 3, p is equal to 3, and can you get to a similar reasoning? Let's see what reasoning we have here. So we have a cubed is b factorial plus 3. Okay, let me try. b is 1, fails. Why? It fails because I get a cubed is equal to 4. That's just not the case. I'm missing an extra number, an extra, what's called power of 2. b is equal to 2. A cubed is 5. Again, I failed. Missing 2 other 5s. b is equal to 3. I get a cubed is equal to 9. Why do I fail here? I have 1 3, and I'll keep getting 3s. But I need to have, if I have 1 3, which I have now, then I have 3 divides this side, so 3 divides this, so 27 divides this. So I need to have 2 more 3s, which I don't, on this side. And then b is equal to 4, it gives me a cubed is 24 plus 3, which is 27. Okay, this is good, so we have another solution. 3, 4, 3. Okay, b equals 5 gives me a cubed is 120 plus 3, 123. Now, why does this fail? Is a question I could fail. Like, we know it failed. Okay, this is now 3 times 41, and 41 is a prime. This makes a cubed humongous. That's not really why this is failing. Like, that's going to be a mystery later on. And what about b is equal to 6? Will it give us a solution? And pause for 2 minutes, and the answer is no. Why? Well, now, if b is greater than or equal to 6, then 3 divides b factorial plus 3, which is equal to a cubed. So 3 divides a, in other words, 27 divides a cubed. Or actually not even 27, 9 divides a cubed. I don't even need 27. And now 9 divides b factorial. From here, I have that. Combine these two facts and we get that 9 divides 3, a contradiction. Now, my question for you is this. This thing that we've done so far, just mind you, just playing around with b is equal to 2 and 3 and solving it. Does this give you an idea for something in general that we may be able to do here? Something in general that we may be able to say, given a prime p, some limits on what b can be? Pause for 5 minutes and think about that. And now that when I clear this up, the answer is, if b is greater than or equal to 2p, then what do we have? Well, we have that p divides b factorial. Okay? And it divides then, now this implies, it divides p divides b factorial plus p, which is a to the power of p. This implies that p divides a, and now p squared divides. And p is greater than or equal to 5. We've solved the cases for 2 and 3. So p squared divides a, and p squared also divides b factorial. I could also write this like this. And these two combined tell me that p squared divides a to the power of p, a to the power of p minus b factorial. So if x divides y, x divides z, x divides y plus or minus z. So this thing is equal to p. So I get p squared divides p, a clear contradiction. Just like that. And what have I done now? I've shown that if p is greater than or equal to 2p, there's no solution. Write these things down. I cannot stress this enough. Finding a solution, this may be worth a point. Combine that with this, you may be able to get 2 points. And if I recall correctly, I think 23 was the cutoff for bronze medal or so. And mind you, if you've solved everything else, like if you've solved questions 1, 2, 4, now you have a medal, right? So, and you want to write stuff down. I've said this before in some videos. You want to maybe, an idea is have a final paper that you're submitting as your paper with facts, right? If you don't have any, if you don't really have, even if you think you've solved the problem, just put a paper with facts on. It can really, really be helpful. It was helpful to one person that on a test that I was coordinating, so do that. Now, let us continue on with our problem. We have this, and now, okay, we know for this implies if there's going to be so b is less than or equal to 2p minus 1, okay? So now, okay, do we have any other ideas? How do we solve the rest of the problem, really? I'm not so sure that I have the next idea. So what will I do? Play around. That is exactly the case. Now let us go to p is equal to 5. See what is happening with p is 5. And mind you, now with p is 5, I have a to the 5th is b factorial plus 5. And okay, I know b is less than 9, less than or equal to 9, but I still have a lot of cases that I don't want to calculate 9 factorial. Please don't make me do that. That's not what I want. I'd much rather, first of all, how do I deal with the cases that are, I think there's like a difference here that I'm getting. If b is less than or equal to 4, it's sort of one type of problem. If it's between 5 and 9, it's like a different type of problem because I have, this is divisible by 5 or not divisible by 5. And there is a little bit of a change there, right? So with that, let us continue on. Onwards, we have, okay, say, we do know how to solve this. I'm not so sure. So let us try b is 1. What happens? A to the 5th is 6. Hey, it's just not working out. But why? Let's think about why. It's small. Okay, is the argument it's small generalizable? For example, if here I have b is equal to p minus 1 factorial, do I really have an argument for large primes that this sum is small? Is that really the argument I'll be making? Nah, it doesn't. It's big enough. Yeah, it's less than 2 to the power of p. So, it doesn't seem like the argument that could stick everywhere. It might be less than 5 to the power of p. It gets messy after that. doesn't seem like an argument that we can really just make there right away. So let us continue onwards. B is equal to 2. What do we get? A to the 5th is 5 plus 2, which is 7. Okay, if it was a 7, it would be at least 7 to the power of 5. Maybe there's something with, the prime factors here. Okay, here we had factors of 2 and 3. Here we had a 7. That's not in B. Maybe that's something that we have to deal with. B is equal to 3. Then what do we have? We have A to the 5th is 6 plus 5, 11. Again, like it's a new factor, bigger than P, bigger than B in this case, bigger than everything. I mean, here it wasn't bigger than P, it was just bigger than B. Maybe, and then this was just and then it was too small. Maybe that's a combination of arguments we need to make. Who knows at this point? If you have any idea, you should pause and try to push the problem further all by yourself. So now what do we have? B is equal to 4. A to the 5th is 6 plus, actually no, 5 plus 24, which is 29. I'm getting a new factor here. And I need to have this at least 29 to the 5th. And that's actually pretty decently, obviously bigger than 4 factorial. Most obvious, I'd say. Now that's this case. And now that we have the visibility, now we have, if B is 5, I know then A is also divisible by 5, so A is at least 5t, right? So then I have, this equation is 5 to the 4th times t to the 5th is equal to b factorial over 5 plus 1. And now I might even be able to get away with a size argument. So for b is equal to 5, what do I have? I have 5 to the 4th, t to the 5th is 4 factorial plus 1. Yeah, this is a straightforward size argument. This is bigger than this. Though even times t doesn't really change anything. So b is equal to 6. What does that give me? Now I have 5 to the power of 4th, t to the power of 5th is 6 times 4 factorial plus 1. The size idea is getting a lot more. It's not really working out for us just here. Just the pure size that this is much bigger than this. Especially if I add in a 7 and an 8, I'm having a much harder time. Actually, then I don't think I just think I plainly don't have the estimate. This is 625. And I need to figure out a different sort of way to go about this. Why is this not -1 modulo 5? Who knows? Maybe that's an argument to be made. And then I have 6 is 1 modulo 5. So, it works for 6, but maybe 7. I'm multiplying it by 2. So it doesn't work. I know 4 factorial is -1 modulo 5 by Wilson's theorem. Seems a bit generalizable. And then I had 6 I can add to it. But then 7? I know if I had a 7, then it's going to be okay. But at some point, I don't know if is 7 times 8 times 9, is that 1? Right? What does that give me? And I'm thinking more in general terms as well, because we have to think about both of these at the same time. For example, we had p is equal to 11, and we had 10 factorial is -1. That's great. We have then a 12. Okay. But then is 13 times 14 times 15 congruent to 1 modulo 11? All of these have their inverses. Maybe there's a word to pair them up. We can maybe say the amount of solutions that exist there, but it doesn't seem like we can really grasp anything. And also, mind you, we're getting into a little bit of a complicated territory now. After this that I've said here, the only way forward would be to go more complicated. And here's another heuristic that we're using when we're solving problems is start simply before you move towards complexity. That is also what you want to keep in mind. So now with this thing just doesn't seem to be working. Maybe 5 is a bit of a difficult one, especially for 6. How do I even think of, like, I'm not getting any ideas. Maybe we need to just focus our attention on the smaller ones, the less than or equal to p minus 1. See if we can gain any ideas on that. Because here's the thing. If we gain some ideas here, we may get some points. It seems a bit easier. It seems like there's something happening here with divisibility that's more closer to home than this thing right here. I don't have any divisibility popping out just yet. Like, what factors does this have? What is this t looking like? I don't see it. So, with this in mind, I invite you to pause for another 10 minutes. And now let's try p is equal to, say, 11. And let's try to deal with these smaller cases for p is equal to 11 and then b less than or equal to 10. Like for numbers 1 through 10. Why does it fail? Pause now, and here's the board after I clear everything up. And now that we've cleared everything up, I want to go to p is equal to 11. Okay, so let's see what's happening now. We have 8, the 11th is b factorial plus 11. Okay, let's say b is less than or equal to 10. What do we know about this side? Well, we had some things with, we had some weird, some factors showing up here, that if they showed up here, the number would just be way too big. Like that, like we had a 13. Here we're gonna have, we plug in a 1, we're gonna have a 12. So here now we have a, that means here that we're going to have a free end. I think even just like looking at the first couple of ones doesn't make sense when we have an 11. Then we can actually just like say there's a size argument there. But I mean, starting from say 5, I'm gonna get 131. That's a prime number. Yes, that's a prime number. So, and that's a new factor here, and that just makes this side, it's a new factor that's hasn't anything to do with 11. It's very much bigger than 5. So let's see if we can maybe formalize this thinking. What is happening with the factors here? Maybe that's a thing for us to look at. And if you've paused, I hope you have that, you've seen that. Now, if A and B, what happens if they share something in common? So B and 11 have nothing in common. B is less than or equal to 10. So A can't be divisible by 11. We know that's not the case. Again, sometimes you need to go back to the basics. And if a number P, if a prime number, say Q, is less than or equal to B, then Q cannot divide A. Right? Because if it did, like this whole number is now going to be what? If B is greater than or equal to 2, this number is odd. 2 can't divide A. If B is greater than or equal to 3, this number is not divisible by 3. 3 can't divide A, and 2 again cannot. So, if a prime number, A is going to have some prime factors, because it's bigger than 1. So, if a prime Q divides A, this implies that Q is greater than B, strictly greater than B. And now maybe there's a way for us to use some size arguments. So if Q divides A, like A is at least Q, so then we have A to the 11th is equal to, B factorial plus 11. This is at least Q, and Q is, it's at least B, so I mean it's Q is greater than or equal to B plus 1, right? We want to, when we're dealing with the integers, we want to use stronger estimates like this, because we can. So this is greater than or equal to Q to the 11th, which is greater than or equal to B plus 1 to the 11th. And now my question for you is, does this fail? This is less than or equal to 10 to the 11th. Actually, I don't want to estimate it with that, but now b plus 1 to the 11th is strictly greater than b to the 11th plus, so that's when I'm taking the b to the 11th part. And then I have 11 times b to the 10th. And this is where my 11 is at. This is greater than b to the greater than or equal to b to the 11th plus 11, if b is equal to 1 being the equality case. And now what do we have? We have this side is strictly greater than this side because of this sign. So now, why is this a contradiction? Well, b to the 11th is bigger than b factorial because b is greater than or equal to b is greater than or equal to b minus 1 all the way till b is strictly greater than 1. We have b terms here, and b is less than 11, so when we multiply these inequalities through, we get this is less than, what's it called, b to the power of b plus 11, and you can say even less than or equal to, and this is less than or equal to b to the 10th plus 11, which is, I mean, I can treat 1 as its own case. b is equal to 1 fails because b plus 1 is not a power of a to the 11th. A would have to be 2. 2 to the p is bigger than, just because then this would be, like, we can treat b is equal to 1 as a separate case in this estimate. Even that's not necessary really, but we could do that. And so now this is, what's it called, giving us the desired contradiction, b to the 11th. Actually, I just need to less than or equal to, so I have a strictly greater than here, b to the 11th plus 11. So here is where our contradiction is. Just like that. We have x is strictly greater than x, and a contradiction. Now my question for you is, can you generalize this? Pause for 10 minutes and try to generalize this. And here is the generalization to all primes. Okay, so now let's go. If b is less than p, then b factorial plus p is equal to a to the p. We know that if q divides a, that implies q does not divide b, because p does not divide b factorial implies, like this implies p does not divide b factorial, which implies that p does not divide a. So q divides a implies also q does not divide b factorial in fact, which implies that q is strictly greater than b, which implies that q is greater than or equal to b plus 1. And now, as we've done before, b factorial plus p is a to the power of p, which is at least q to the power of p, which is at least b plus 1 to the power of p, which is strictly greater than, mind you, p here is greater than or equal to 5, strictly greater than b to the power of p plus p times p to the b minus 1, greater than or equal to p to the b plus p. And now we get our contradiction because this thing is strictly greater than b factorial, greater than or equal to, I'd go with greater than or equal to b factorial plus b. We have this strictly less than this, and that's a contradiction. Okay, and now what have we done? Mind you, we've done this through getting an idea for how to solve smaller cases. That's the big thing that I want to get you to see from this problem is, yes, there's this technique that we're going through, very nice, very cool, very dandy, but also what we're doing at the same time is we're using small cases. We're using the fact that when we're lost, and we're often lost in problems, we're using this heuristic that helps us find our way back. And that heuristic is play around with something small that you can handle and try to see how you could generalize that. There was an idea that we thought about with Wilson's theorem that we're not using yet because it's too complicated, but we're going down a path and we're saying, no, it's too much. I'm playing, I'm generalizing, okay? And I'm going to fail a couple of times. And that is something that you should expect when you're solving problems. And with that in mind, let us now continue. We now have that B is so B needs to be greater than or equal to P, less than or equal to 2P minus 1. Now, what happens if B is here? It's a very specific interval it's in. It means that only 1P divides this. What does this mean for us now? Pause for 10 minutes and try to push it further. I mean, in fact, what I would do is I try to see if P is equal to 11. Tell me, why is a to the 11th not equal to, and I'm assuming it's not here. I'm assuming that these are really going to be my only solutions unless I've missed something on a 5. But I'm assuming that there are not these exotic solutions here. There might be, but for now, I'm assuming they're not. So I'm thinking that this equaling b factorial plus 11. Okay, why does this not have a solution? But let me ask you something more specific. Why is 15 factorial plus 11 not equal to a perfect 11th power? Like, why not? Why would that not be the case? Well, maybe it's okay. Let's say instead of 15, let me do something even like bigger. Let me do something like 19 factorial. It's a prime, you know, sure, play around with it. You really can't use Wilson's theorem on this, but go ahead. What would you do here? Please pause, at least for 5-10 minutes, try to solve this one. And okay, the trouble is, okay, we know that this is divisible by 11. Okay, so 11 divides A. We know that bit. Now, what else divides A? Okay, think about this. Well, can 11 squared divide A? Well, if 11 squared divide A, yeah, that would be cool. Sure. No problem. What else could divide A? Is that a question? What if a prime Q divides A? Something similar to what we've seen here. What can we say about this prime Q? Okay, pause for 2 minutes, think about that part. And the answer is, well, we can say about Q that if Q was less than or equal to 19, then we have Q divides A, Q divides this, Q divides 11. A contradiction. So if a prime Q not equal to 11 divides A, that means Q is greater than or equal to 19. So if it was the case that Q, some other prime, divided A as well, we'd have this A is at least 19. And now this seems like we could really do a size argument. Now we'd have that this then is at least, in that case, we'd have this thing is at least 11 to the 11th times 19 to the 11th. I mean, in fact, strictly greater than this. Or I could even say like greater than or equal to, I'm also thinking in terms of generalities, 20 to the 11th. Okay, like plus 1. If this was 18, this would be at least, 19. And I'm thinking like this is an estimate. I can also generalize. That's what we're thinking about at the same time. So, okay, 11 to the 11th. Now, why is this? So this is 11, like there's 11 things here multiplied together. Okay, but I can say, okay, 11 is greater than 1, 11 is greater than 2, 11 is greater than 3, and 11 is greater than or equal to 11. This deals with the first couple of numbers. And then the 20 is greater than 12, is greater than 13, greater than all the way till 19. Okay, and how many things do I have here? I have 19 minus 11 things, so that is 8 things here. And I'm well over bounds here, right? I'm well in the clear. I can even write this as this minus 1 plus, I mean, like we still need to say, okay, why is this not equal to, like this is now strictly less, now we're going to show that this is strictly greater than 19 factorial. Oh, but I have, now this is greater than 19 factorial. And then I still had a couple of 20s left. I had at least one 20 left, times 20. And now there's a clear contradiction. 11 is greater than 19 factorial times 19. Nah, that's not the case. Now the question is for you, could you find a way to generalize this sort of thinking? And maybe a much more specific question would be, under what conditions would you be able to do that? And here's also a thing I forgot to mention. I just said here, if there's another prime dividing this. But it could be that only 11 divides A. And that A is equal to, in fact, A is equal to 11 to the power of T for some T. And then what we would have here is 11 to the power of 11T is equal to 19 factorial plus 11. Okay, let me divide this by 11. Divide by 11. 11t minus 1. And now this transforms into 11 to the power of x minus 1 is 19 factorial, where x is 11t minus 1. Okay. Now here for me, I don't know, but for me, what does this sort of tell you? Well, if t was, say, 4, I could probably do a size argument that this is bigger than this. And if t was like at least 4, I could say 11 times 11 is bigger than 19. I mean, actually, I need at least a 3. I'd have 11 times 11 is bigger than 19. 11 times 11 is bigger than 18. I know these are horrible estimates, but they would work. And then t is equal to, what's it called? T is equal to 2 would be sort of an edge case here. And I'd be thinking, I mean, you know, maybe t is equal to 2 could work. Potentially. Like that would be, wait, that would mean that this is 121 to the power. Like that just feels wrong for it to work. Let's just, let's actually just check this out. If t is equal to 2, can we just do a size argument to begin with without going into this thing? And for t is equal to 2, we'd have 11 to the power of 22 is equal to 19 factorial plus 11. Okay? Now, 11 to the power of 22. Okay, now what can we do here? This is also just like, useful technique. I have 11. This is as if I had 11 times 11 times 11, 11 to the 11th squared, but I multiplied everything twice. This does not make a lot of sense, but here's what I'm trying to get at. I have 11 times 11. Instead of saying 11 is greater than something, 11 times 11 is greater than 19 times 3. Why do I know this? And not just this, it's greater than 12 times 10. These numbers have the same sum. If I get to 11 times 11, like if x plus y is a constant, then the product xy is maximum when x is equal to y. And I can use that, in fact, to just estimate this as 11 times 11, and I start from 3, I go up to 10, and that gives me 11 to the power of 8 times 2 is bigger than this, and now I need to multiply by, so this is 11 to the 16th, multiply by 1 to get 11 to the 17th is greater than 19 factorial over 2, right? And from here, this is becoming laughable. If I do, then 11 to the power of 18 is bigger than 19 factorial. And again, I can come up with an estimate. It's a question whether we can do this now in general. But it seems if we could do this for 11, we might even just be able to use that estimate for any other prime p. And here's where I invite you to pause for the next 10 minutes and try to see if you can handle this case now delicately. What does this case sort of force for you? Okay? And here's the next step after I clear everything up and the stuff we've done here. So next step is, so now the next step that we're going to go to, if q divides a and q is not equal to p, or p squared divides a, what do we have? Well, if this is the case, this implies that q needs to be greater than b factorial. Q cannot divide b factorial. And so we have that from here, q is strictly greater than b factorial. I mean, it's strictly greater than b. And because it's strictly greater than b, it's greater than or equal to b plus 1. And with this part, if p squared divides a, then this implies that a is greater than or equal to p squared. In any way, let's say a is equal to p times some t. This implies that t is greater than or equal to p. And this thing here would imply that t is greater than or equal to b plus 1. So in any way, t is greater than or equal to the smaller one of these. In other words, t is greater than or equal to p. And now what do we have? We have pt to the power of p is greater than or equal to p squared to the power of p. And here I have 2p minus 1 factorial plus p. This is going to be equal to, first of all, like going to be equal to b factorial plus p, which is less than or equal to 2p minus 1 factorial plus p. This is the biggest this can get. And now what do I say? Well, I say I have, how many pairs? I have p times p is strictly greater than p minus 1 times p plus 1. And I go all the way till p times p is strictly greater than, what's their sum? Their sum is 2p. 1 times 2p minus 1. Okay, I have all of these facts. How many facts do I have? I have p minus 1 facts. When I multiply these inequalities together, I get this is strictly greater than p squared times 2p minus 1 factorial over p. In other words, this is strictly greater than p times 2p minus 1 factorial. And now, this thing is strictly greater than 2p minus 1 factorial plus p. And here's my desired contradiction. And now, what does my contradiction imply? Right? And also, why is t greater than or equal to p in both of these cases? Well, b, we've said, is greater than or equal to p. So b plus 1 greater than or equal to p plus 1 greater than or equal to p, but it's greater than p. And this just, finishes two birds with one stone sort of thing. So this part, also, mind you, it's a step-by-step process, and now we're left with really saying that if this is the case at some point, then a is in fact equal to p. So we'd have that p to the power of p minus 1, actually no, p to the power of p is equal to b factorial plus p. This needs to hold true. And also, we've not really used much of the bounds for 2 and 3, but this is, consistent with what we've found with some small cases. Also, another reason why it's important to play with small cases is because, now you get to do a sanity check here. And with this in mind, we've done our sanity check. We have, if the initial problem condition was true, then this needs to be true as well. And now that this is, I think this is pretty cool that we're this far into the problem. And now with that, we also might just need to do a to the p minus 1 is equal to p. Why does this fail? It fails because this is much bigger than this. That's one way we can go about this, but this is a minus 1 times a to the p minus 1 plus all the way till a plus 1. This thing over here, it has p things in it. This is divisible by, like this thing here is greater than or equal to p, right? And it's equal to p only if p is equal, if a is 1. But then this is 0. So it's greater or equal to 2 to the power of p minus 1 plus all of these things. And this is strictly greater than p. And then this is at least 1. This whole side is greater than p. So we discard that case. That was just like a thing, I think, that I glossed over initially. Why b is equal to 1 doesn't work out either. I just felt it was necessary to do that. Maybe I'm wrong. But now, this is our problem. P to the p is b factorial plus p. How are you going to solve this one? Pause for 10 minutes. Think about it. Why is 11 to the 11th not equal to b factorial plus 11? For some b that's, less than or equal to 21 and greater than or equal to 11. Pause now and think about this. And here's the next step. And now that we've cleared everything up, let's really, divide everything by 11. We have 11 to the 10th. Now minus 1, now I can write this as a difference of, what's it called? A difference of squares, I think is the correct term, is equal to b factorial over 11. Sure, this is divisible by 11. I don't really care about it. But this thing is now 11 to the 5th minus 1 times 11 to the 5th plus 1. And I can now further factor this into 11 to the 11 minus 1 times 11 plus 1 times 11 to the 4th plus 11 to the cubed plus squared plus 11 plus 1 times this minus this cubed plus this cubed minus 1 plus 1. Now I could go ahead and try to prove that this actually, that one of these two things has a factor that's greater than or equals 23, a prime factor. Yeah, it's probably, I think it does, but how can I generalize that? Like, that's my question all the time that I'm asking myself. What is it here that I can actually generalize? And okay, so I know stuff around this, and in general, I'll be able to, deal with p minus 1 and p plus 1. And I might be able to figure out something that's true for this, something. Well, okay, let's see. What do we have? Well, this is 10 times 12. Okay, maybe one of these will be divisible by 3. But these numbers are what modulo 3? So 11 is a 2. So I'm thinking one or the other. So 11 squared is going to be a 1. Modulo is going to be, a 1 modulo 11. These are going to be 2's. 2 plus 1, 2 plus 1. This is a 1 modulo 11. And this is 1 plus 1 plus 1 plus 1 plus 1. Again, a 2. That's modulo 3, I'm saying. Modulo 3 on both of these. So only this is divisible by 3 versus this divisible by 9, a contradiction. Okay, so maybe 3's I can look at. And if I'm going through factors, I might as well also look at 5's. Not 5's, but 2's. Like they have just evens and odds. And I know my primes are odd, so I can maybe deal with that in an easier way. And if I have, has 1, 2, this is divisible fully by 8. and it's divisible fully by 3. So, and why is this fully divisible by 3? I'm still not sure I understand why that part is the case. When I take it down to its bare components, how many 3's will I have? Like, that's another question I could be asking myself here. Maybe there's not, I don't know if there's a bound maybe there or not. We'll see. Like, this is an interesting, way of thinking. And now what I'd do here is I'd start with 2's, because 2's I know the formula for it. I mean, I know the formula for 3's as well, for any prime for this. But 2's is my simple idea. I'll maybe move on to 3's later on, if there's not much to do with 2's. But I guess that 11 fails here because I have 8 divides this, but this thing here is at least, this thing here is divisible by 11 factorial over 11, which is 10 factorial. And now this thing over here, 10 factorial, is divisible by 16 because it has an 8 and a 2. So maybe that's the big idea. Maybe this side has more 2's than this side. And that might finish the problem. So, let's try to actually, play around with this a bit more before we try to, generalize this to this equation over here. So 13 to the power of 12 minus 1 is equal to 13. So this is 13. This is 3 times 13 cubed plus 1, 13 cubed minus 1, and 13 to the power of 6 minus 1. I just did a successive application of a difference of squares here. And now this is 13 to the 6th plus 1. And I can't factor this anymore. Now this is 13 plus 1 times 13 minus 1 times now 13 squared plus 13 plus 1 times 13 squared minus 13 plus 1 times 13 to the 6th plus 1. Okay, how many 2's does this have? These are odd, as before, just like these were odd, so there's no what's equal to 2's to be found there. The trouble is with this number, how can I not explicitly figure it out? It seems like, oh no, what do I do? But you do modulo 4 or modulo 8. An odd number to the even power is 1 modulo 4. So that plus 1 is 2 modulo 4. So this one has 1 2. And this is just divisible fully by 2. And now this is fully divisible by 4. So this is 14. So this is, again, just 1 2. And now this is 12, which gives me 2 more 2's. So I have 4 2's here, 16. But again, this is divisible by 32 as well. This is by 2 times 4 times 8. It's big enough. So it seems now I'm going to have a lot of 2's on this side that I won't be able to just catch up. That's what it seems to me to be the case. And if I even do 17 to the power 16 minus 1. Now this one is interesting because I'll be able to do this thing many times over. I'll have this is 17 minus 1 times 17 plus 1 times 17 squared plus 1, 17 to the power 4 plus 1, 17 to the power of 8 plus 1. And yeah, that's about it. So this has a 2, a 2, a 2. 18 has a 2. And then 17 minus 1 is 16. So that's 2 to the power of 4. This is an interesting contender because this is now 4, 5, 6, 7, 8. 8 2's, so 2 to the power of 8 fully divides this. Do I have 9 2's? Well, if I'm looking at 16 factorial, as I am looking at it there, this has a 2 times a 4 times an 8 times a 16. I am way over it, way over 2 to the 8th, just with these numbers. So again, it fails. Now, can we generalize this? pause for 10 minutes, generalize it. Here's the generalization. And now we're looking at the generalization. Also just for 7, because we've figured that we've solved all the primes that are less than or equal to, 17 now. And 7 I just want to solve with like 43 divides this side. And it does not divide this side, so it's done. And also maybe 5, we'd also need to say why 5 to the 4th minus 1 is not equal to b factorial over 5. So this thing is 5 plus 1, 5 squared plus 1, and 5 minus 1. So this has a 13 in it. This is 26. So this is divisible by 13, but this thing over here is not. And so this also doesn't work out. Now, for this part, what do? Well, we have how many powers of 2 here? And now, if p minus 1 is equal to, say, 2 to the alpha times some k, then we can write this as p to the power of 2 to the alpha times k minus 1, which is, applying this operation successively, p to the alpha minus 1k plus 1 times this minus 1, which is p to the 2 to the alpha minus 2 times k plus 1, so on and so forth, until we reach p to the 2k plus 1, and then p to the k plus 1, p to the k minus 1. Now all of these have 1, 2 in it, and then these two are p plus 1 times something odd times some 2t plus 1 times p minus 1. So when I multiply these, the other two parts, they are odd, they have 0 2's. So now the amount of 2's that this has, this number over here, is going to be equal to, so this is alpha minus 1, this is 2 to the first, so 1 through alpha minus 1, so the total number of 2's is alpha minus 1, okay, and then plus the number of 2's p plus 1 and p minus 1 have. So alpha minus 1. And now how do we actually write this down? There's a what's called a function that's generally used. v2 of x tells us that how many 2's there are in x. In other words, if this is equal to some, say b, capital B, that means that 2 to the b divides x and 2 to the b plus 1 does not divide x. And this is just a shorthand for this. So v2 of p times p to the p minus 1 is equal to alpha minus 1 plus the number of 2's that are in p minus 1 plus the number of 2's that are in p plus 1, which is incidentally alpha again. So this whole thing, the number of 2's here, is in fact, I'll write it here, equal to twice the number of 2's there are in p minus 1 plus the number of 2's there are in p plus 1 minus 1. Okay, so that's the number of 2's we have here. Now, that's all fine and cool, but it's still a large number. And how many 2's do we have here? Well, on b factorial, well, we have the number of 2's for b factorial is at least the number of 2's we have for p factorial. And we've shown that this usually was bigger. Now we could maybe estimate what this can be. One quick estimate I'm thinking of is that what's called if p is between 2 to the beta and 2 to the beta plus 1, maybe minus 1 and 2 to the beta. I'm just thinking which one will give me a better estimate. I know that this thing here is going to have 2 to the beta minus 1, 2 to the beta minus 2, all the way till 2. So it's going to be at least equal to 1 plus 2 plus all the way till plus 3 plus all the way till beta minus 1, right? That's what this is going to give me, if I'm not mistaken, yeah? So that's on one hand. This might be a horrible estimate, it might not be. And on the other hand, we also have that, mind you, this alpha times k. Like k is at least 1, and alpha is at most beta minus 1. So, okay, so now I'm thinking instead of beta minus 1, I might just do beta here and beta plus 1. So now this whole expression here we can estimate, and also the number of 2's in p plus 1 is at most beta plus 1, and this is an estimate that will never hold true. So now all of this is strictly less than when I combine these two estimates. So I get that, or this thing over here I should say, is strictly less than 2 times beta plus beta plus 1, 3 times beta. And on the other hand, the number of 2's here is at least beta times beta plus 1 over 2. And we have this is strictly greater than this. In other words, 3 is strictly greater than beta plus 1 over 2. In other words, 5 is strictly greater than beta. So P needs to be less than, for this whole thing to hold true with our super weak estimates, it needs to be less than 64. Now, we could just, play around, like just finish all these cases manually. Well, there's a bunch of primes that we haven't looked at, 17, we've looked at 17, but now it's 19, 23, 29, 31. If it was 32, I can live with that. I can just do 32, that's okay. But I really don't feel like going all the way till, 61? That's my final prime there. Don't feel like, looking around all of those primes. So instead, let's get some better estimates, because this was a horrendous estimate, mind you. This is not just strictly less than 3 beta, it's probably less than 2 beta plus something. So let's think about this in a different manner. This is still okay. The number of, so we can have, 2 cases. Case 1, 2 fully divides p plus 1, because 2 will, one of them is only going to have 1, 2. So let's say p plus 1 only has 1, 2. So the first case. And then this is 2 times v2 of p minus 1. And now this is less than or equal to beta times 2. And now, on the other hand, this is strictly greater than, because I'm missing a 6. I'm not counting that 6. Strictly greater than beta times beta plus 1 over 2. Cancel the betas. I get beta plus 1 is less than 4. Beta is less than 3 in this case. Okay, so in this case, beta is in fact less than 3, which means I only need to check p's that are less than 16. I've already done that. And in the second case, which is arguably the worst case, second case is if 2 fully divides p minus 1. Then what do I have? I have here, this is v2 of p plus 1 plus 1. This is again now strictly less than what? Beta plus 1. At this part, I don't even think this matters. And it can't be beta plus, maybe it could be beta plus 1 under some cases. Doesn't really matter if we can deal with this nice. Strictly less than or equal to beta plus 2. And with that, we have this is less than or equal to this. And so this part now needs to be beta plus 2 needs to be strictly greater than beta times beta plus 1 over 2. I could even say like I'm dealing with primes that are, if my p is greater than, what's it called, 16, then I'm sort of dealing with what? What is my b factorial going to, is it going to include a 10? That's the only thing I'm really interested in. Then yeah, b is greater than or equal to p, so it's going to include a 10. So I have at least this plus 2, because I haven't counted my 12, right? I only counted my 6 and my 10 and my 12, and I've not counted the 12. So now I have, this needs to be the case. In other words, betas then cancel out, or what I'm left with is 2 needs to be greater than beta plus 1. And I've dealt with this case as well. And that finishes up our casework. You know, we've needed to do some level of analysis here, dealt with some evens and odds cases to finish everything up. What I like about this problem is, you know, it's a number theory problem at the IMO. And this year's IMO, really the problems 1, 2, 4, 5 were all in, you know, number 1 was combinatorics, pure combinatorics. The second one was a pure function. I really like it. The fourth one was a geometry, plain as day, and this is a plain as day number theory. You might say, okay, it's not super great, it's pretty linear, but I disagree. I think it's still cool enough to get to the IMO, because it as a number 5, okay, you could say maybe it's too easy. I would have said maybe. It's like, it really depends on your taste. It bears resemblance, like this idea of bounding with factorials and looking at the numbers of 2's was similar to what I think was 2019's problem 4 or 2018's, one of the two. And that's why it's important, you know, to look at past year's IMOs. I mean, shortlists as well are a fantastic use of knowledge and different types of solutions. I haven't seen, you know, like other solutions try to, you know, really do a similar version of this. I haven't seen anything with Wilson's theorem. That could be cool, you know, with this case, be between here. Is there something we can do with multiplicative inverses? Who knows? But this is a pretty cool problem, very technical in nature. I hope you've enjoyed it. Let me know if you have different ideas at some places, different ways you would finish it up, or anything you think differently. Any other motivations you had that were different from mine. You know, I tried to motivate this also for you, as though like I know nothing about number theory except how to, you know, play around some small cases. Because I really think that if you do that, it really helps ground you into an easier problem, which you can then generalize from. This finishes up our whole discussion on this problem. And as always, thanks for problem solving.